you very much. Thanks for the invitation. Both to come again to this beautiful place and to present some work. So I was reading the description of the workshop, and it says something like bringing together equivariant people and motivic people and various things. And I thought maybe not everyone is going to be motivic, and so then I can just tell them something about equivariant motivic, and they will find it interesting. Okay, even if it's not, let's say, cutting edge new results like we have seen in some of the other talks. And well, I feel like the first part of my calculation was correct. Not everyone here is a purely motivic person. You will have to judge the second half, but but we'll see. Okay, so basically, like I'm gonna pretend that all of you know equivariant homotopy theory essentially perfectly, and basically you want to mesh it together with motivic, and you do some obvious things. And then you think, well, it's all the same. But the problem is it's not all the same. Some things are different, just like ordinary motivic homotopy theory is not quite all the same as usual homotopy theory. And I want to show you some of the differences. Now, I mean, there's a large body of work on equivariant motivic homotopy theory, and I'm definitely not going to be doing it justice. So it's going to be some kind of selection, which you might call eclectic, or some other word with E, I don't know. Okay, so what are we going to do? We are going to work over some scheme S. And I think if you take the spectrum of a field, maybe even algebraically closed, it's already interesting. But for now, I'll just take any scheme. And then, of course, I mean, I need to do some equivariant business, so I need a group. So I will give myself a group scheme. Okay, and so my basic business is that I want to make a homotopy theory for schemes over S with an action by this group G. Okay, so maybe to get one thing out of the way is that, of course, whenever you're talking about things with an action, you could be talking about stacks instead. And everything I say, you could translate it into something about stacks. So just relate it. You could try to make a homotopy theory of stacks. And so the way this works, of course, is that if you have your x, as I was saying, you have your x over s with a g action, then you take the quotient stack, which I might denote by x, homotopy quotient g. Algebraic geometers might denote it by something like this. In any case, the same object. And then you can talk about things somehow happening over this stack, which is the same thing as things happening over x with a compatible g action. And so my goal will be to explain some sort of genuine equivariant motivic G something category. So this guy. And if you're a stacky person, your goal might be to explain something like this guy. And of course, they will be the same. Okay, so in some sense, we're just in the business of describing the homotopy theory of certain particularly nice stacks. And I mean, you can then ask yourself, can you extend it to more stacks? And yes and no, it gets more and more complicated. I've chosen to use this language. All right, so now recall, okay, we want to build this category, and I will just, in like 5 seconds, remind you how the usual motivic stable category is built. Okay, so you start with some sort of building blocks, and the building blocks are the smooth schemes. Okay, and then you want to allow yourself to do some amount of category theory. Right, you want to have colimits and stuff. And so what you do then is you look at the category of Nisnevich schemes. Okay, there's some subtlety, of course, why do you want in this neighborhood topology, why not, but I'm just going to ignore this. This is some category theory nonsense to start with this one category, which is just pure algebraic geometry to make it more homotopical. And then, okay, you need to mesh the two somehow, and the way you mesh it, of course, you know, you just declare that the affine line should be contractible and see what happens. This is called the category of motivic spaces. And now you want to be stable, so it turns out the correct thing to do is to invert the Riemann sphere. Which is, of course, the projective line. And this is SH of K. Okay, and so the basic point is, if you want to construct this category, you want to follow this recipe to some extent. But of course, I mean, you're not, like, this recipe is not out of thin air. It's justified by the fact that this category here has very good properties. In particular, if you vary the base field or the base scheme, then you get something called the six functors formalism, so you get a good theory of duality and so on and so forth. And the fact that you get all of these things out, somehow at the end they justify these somewhat arbitrary looking choices. Okay, you could do other things. Maybe you arrive at a similar category with also good properties. Maybe you even arrive at the same category. I don't know, but yeah, definitely you want it to be well behaved, because at the end of the day, you want to do something and not just write down some definition on a sheet of paper. That's kind of dumb, right? So I just have to replicate these steps. So the first step was to look at sheaves.
Do you not also need to invert the topological sphere?
But that's built in. So in the motivic world, you have this funny relation that P1 is actually the smash product of the usual circle and sort of GM, which is like the algebraic geometry circle. So if you invert the product, you invert both of them. It's a fun little exercise if you have not seen this before at the talk. Okay, so we start with sheaves. Okay. First question, of course, is sheaves on what? So the answer, of course, is then sheaves on smooth schemes with a G action. So we have this category of what am I trying to say? So I have X will be S scheme with G action. Okay, and then I have the category of X schemes with a G action. That's the obvious thing, right? And inside this, I have the category of smooth schemes. And so you have to contemplate for a second what you want smooth to mean. And I mean, one obvious choice is to say, well, it's smooth if and only if it's smooth when I just forget all about the G nonsense. And it turns out, in this case, that's a good definition. Okay? So this is all those y equals to x, G, whatever, such that y is smooth over x, ignoring G. Okay? And in a similar way, you can define étale morphisms, or open immersions, closed immersions. Okay, and I guess, I mean, ultimately the reason for this is that the map from the point to VG is some kind of covering. And these kinds of properties in algebraic geometry you can check after some kinds of covering. And so then we want to define, yeah, so now we do pre-sheaves on this, of course, and now I want to explain what a Nisnevich sheaf is. And the way that you do it, well, you know, there are several ways of defining the Nisnevich topology using like this completely decomposed covering families or the Nisnevich squares or something like that. And you choose one of them and you generalize it. And again, there seem to be many choices, and hopefully at the end we arrive at something good. And now, of course, I'm going to tell you the correct choice. And the easiest thing, the easiest idea to make correct is to generalize the notion of a distinguished square. So that is quite easy, which is to say that if I have a square like this, I don't know. So this kind of square is called a distinguished Nesnevich square if it is a square. Is it bad to write on this side? If it is a distinguished Nesnevich square after forgetting about all the G nonsense. In other words, this morphism is an open immersion, this morphism is an étale morphism, the square is Cartesian, and if you look at the closed complements of these open immersions, there's some induced morphism, which is an isomorphism, let's say if you choose the reduced closed structure, although it doesn't matter which one you choose. Okay. And so then out of this, in the usual way, you can build your Nesnevich topology. And here is maybe the first time that I give you a warning, which is that you could have said something which sounds equally reasonable and then gives you something else which apparently is wrong. So for example, so these things generate a topology. So these squares, yeah, I mean basically these two together form a covering in the topology, and then you look at the topology generated by these things. Okay, so you get some topology on this side, on this category here, and it's also the case that you have descent with respect to this topology if and only if you have the usual Nesnevich squares condition. So you need to, basically the empty set should be sent to the contractible space, and each of these squares has to be sent to a Pullback square, and then automatically you get your descent. It's the usual magic, is very nice. But this is not the same. So this topology as the sort of obvious thing which you could say, which is to say that a family of maps is a covering if and only if it is a covering after forgetting about G. I don't know.
Could you raise the board?
Okay, so now you're seasoned equivariant homotopy theorists, so this is not particularly surprising because also in the same sort of thing happens in the genuine usual homotopy theory. That, I mean, the point is that you're sort of forgetting about the stabilizers, and then it's just not right. That's not what genuine means. So you say, aha, what I'm going to do is I'm just going to say it should be for every fixed point, right? Let's say it's a finite group so that the subgroups are sort of easy to look at. And you take fixed points, you get some new covering family. Surely, because fixed points of these squares are these squares again, we must require that this is also a covering after taking all the fixed points. But that's still not the right thing, okay? So, okay, so it is possible to describe what, I mean, if you have some family of maps, what is the condition that you need? But I mean, it's not, neither of these descriptions would be correct. So you need to be careful. But of course, if you want to do something with equivariant motivic homotopy theory, you're just going to look at some paper which defines it, and then they will give you the correct definition. And usually you can guess, but my point is you have to look because sometimes you're wrong. Or maybe you look at it, at least when something doesn't seem to work, you should look.
So,
okay.
Sorry, so in this Nesnevich square, so is the difference that, like, you already know that W is the correct thing? Or
What do you mean the correct?
like the...
W is just the intersection of the...
Yes. But so why like intuitively, why is this wrong? The second one?
Maybe I don't want to claim that I have intuitive answer.
Okay.
I mean, you can write down some counterexamples, but
Okay.
I should have prepared for this.
So, sorry, but I want to be slightly more precise. So are these covered in your topology? Yes.
What do you mean? So this kind of cover is a cover in this sense and a cover in this sense, but neither reverse implication holds.
Okay.
So are fullbacks underlined in schemes?
Yes.
Oh, okay. Oh, okay.
So I can write the punchline. So we have our Nisnevich sheaves. And this will be what? It will be and where this Nisnevich localization for our purposes just means that I make all the Nisnevich squares into co-Cartesian squares. But at least under like very mild assumptions, that's the same thing as sheafifying for the topology generated by these coverings consisting of U and V in the above picture. Okay, so we had a recipe which we were supposed to follow, and we got to step 1. Okay, so now we go to step 2. We go to the spaces. Well, this is like non-abelian derived category. It just enforces that the finite disjoint unions of schemes are sent to finite products. And the only relevant condition here is that it sends the empty set to the terminal space. Yes. Okay, so we need to contract something, and I mean the most obvious thing which we can of course contract is A1 with a trivial action. Okay, now surely, I mean, we have to contract A1, but the question is, should there be more? I don't know whatever should means, but you look at the proofs, and it turns out that sometimes you want more. So for example, if you have any vector bundle, you want to contract that. But that's also an obvious consequence, right? Because a vector bundle has an action by A1, and so you can use an obvious homotopy to contract it down. But it turns out that there's something called a vector bundle torsor. So it's something which you want to think is sort of similar to a vector bundle, but it's not quite one. And these things do not, apparently, so I'm also not the best equivariant algebraic geometer, but apparently there are examples where these things also don't have A1 action. So they would not become contractible. But this, I mean, you need to have like positive dimensional groups and stuff, but okay, they're legit. So we need to account for this.
Sorry, class.
Yes.
So you're saying that you won't get the same topology if you take these different coverings, but is there a reason why you choose this and not the other ones, or is that the same question that evolved? I'm not sure.
Could you repeat the question?
So she asks why we should use the above definition as one of the, not one of the other two. Like, I mean, I don't know. This goes sort of similar to what I'm saying here. There's some arbitrariness, but at the end we get a good category. And so we, not me, but people can prove that if you use the first definition, you get a lot of good properties. And if you use the second, I guess then you don't. Problem is that there exist vector bundle torsors without a one action. Okay, and then you say, why do I care about vector bundle torsors? And of course, like, I mean, I'm just pulling this out of thin air, but one example are these so-called Johannes devices, which are very neat things which you can use to replace like quasi-projective schemes by affine schemes. They are sort of technically useful for a lot of things, and they are examples of vector bundle torsors. which is why in the usual motivic world, you know that every reasonable scheme, so any quasi-projective scheme, is actually, you can replace it by something affine up to motivic equivalence, and you want to do something similar here, and it won't work. Okay, but so the solution which Marc Oyoa, I believe, came up with is to just, well, I mean, he just recognized this problem. I was like, okay, with mathematicians, it's very easy to solve this problem. We just contract them all, and I mean, that's the definition. Okay, right, so this declares that this means you declare all vector bundle torsors to be equivalences in your new category. Let me immediately follow this up with a remark, which is that if you have a finite group, then this problem does not arise, and you do not need to concern yourself with it. And yeah, so this, let's see what I was going to say. If G to S is finite, then you don't need to be concerned with this. And for the remainder of my talk, maybe for a while, I'm going to pretend that the group could be anything. But I certainly think more about finite groups than other groups, yes?
What is a vector bundle torsor in this context?
Well, a vector bundle is some kind of group scheme, right? And then it's just a torsor under this group scheme, under addition.
When you say finite group, do you allow finite group scheme?
Yeah. So when I was writing this, I was thinking finite group scheme, but I don't actually remember how you prove this, so you should better check the reference. Definitely true for finite discrete constant groups, but I think it's true for finite group schemes, but don't quote me on that.
You don't need flatness.
I do need
Flat.
Probably flat is built into the definition of group scheme. Pretty soon it's going to be finite et al, and then we're all happy. Oh, I'm not talking as fast as I want to. Anyway, what is the problem? Oh yes, okay. So we have a category of motivic spaces, and now we have to justify why this whole maneuver was a good idea. And as I was saying, the only justification I can offer you is that this has good properties, so let me just assert this. This category has the expected properties. Okay, but then there's an if, and the if is that the group G has to be what is called tame. And I don't want to explain what tame means, but for example, if you have a finite et al group, this means that the order has to be invertible on your base scheme. Oops. Right, and so what you see, what this thing buys you, like in the classical representation for theory, for example, is that you have these projection operators, and they make your life much easier. And basically what it means is that, I think what it means also, what basically the point is that certain fixed points on representations, they're just exact. And if you don't have this, then life is much harder. And I think the motivic equivariant homotopy theory is very mysterious, and nobody knows a reasonable definition. So you can write down this definition, but it will not have the good properties. I will add like one or two in a second. And I don't know how to make a better theory. And I don't think anyone does.
Sorry, can I ask a question? So this column over there,
Yes.
I'm just trying to understand. There's this vector bundle torus is about one action, like without a G, like this is true without the G action.
Yes.
So without a G compatible.
Yeah, of course, yes. A vector bundle torus is in the category of G schemes and so on. Yeah.
Can you say a bit about those kind of properties? That
I'm
you say? Oh,
working. Oh, that fair. Yeah, okay. But I also that, yeah. Okay, so the main properties which you would want is, for example, purity. Which would mean that if I have a closed immersion of smooth schemes, so I have Z into X, oops, maybe Y because I'm working over X. Then I look at sort of the local neighborhood, which is Y minus Z, and you can prove that this is equivalent to some tome space. So maybe I don't want to define the tome space, so it's something like the normal bundle of C and Y modulo the normal bundle of C and Y take away C. Yeah, so this means that somehow Z inside some smooth scheme, it looks like you just embedded it into some vector bundle. So there's some local normal form in some abstract sense. And well, actually, I don't know if this fails in the other category because I haven't thought about it, but definitely the proof that Mark gives will, it for sure uses the tameness. So I suspect it fails, actually. I don't have it. A related property that you want is this localization sequence. Maybe I'm not going to write it out, but yes, that's the kind of properties I have in mind. So then we are at step 2 in our program, and so now we go to Spectra. This is a bit easier. In particular, in the sense that if I tell you to guess what to do, you will guess right. So the most obvious thing, which is not what you would guess. Sorry?
you overestimate us.
Don't overestimate you, Fyodor. So the obvious guess, which is the one which you're not going to make, is that you invert the trivial representation sphere. Okay. But again, we want a category with good properties at the end, and so in particular we want good duality properties. And if you want good duality properties, this usually means that you want these sorts of tome spaces here to be invertible objects. But again, as mathematicians, it's very easy for us to enforce that because, I mean, pick all the vector bundles and we invert them all. What am I doing? Okay, and you can do this, and that is correct, but it's not obviously correct because the following problem arises. The problem which arises is that I want, at the end of the day, to get out some sort of 6 functors formalism. And so, for example, if I make a smooth morphism, y x smooth, oops, then the pullback, it should have a left adjoint, which is called f lower, sharp. Should have. Okay, so on the level of, right, so as far as 6 functors go, this is sort of the trivial one. On the level of schemes, this is completely obvious. Okay, if you take a smooth scheme over y, how do you make a smooth scheme over x? Well, it's already staring you in the face. And what's supposed to happen is that the construction just sort of keeps passing through. There should be an obvious left adjoint. But if here you invert all the vector bundles coming from x, here you invert all the vector bundles coming from y, you're now a bit screwed if you're trying to sort of lower sharp the inverse of some new vector bundle here. Where are you going to send it to? So that's annoying. And the solution is that you don't invert all the vector bundles of x. What you do is you invert all the vector bundles coming from S. Or maybe, yeah, I invert these guys for V isomorphic to V0 times pi over S. X, V0, a vector bundle on S. And I guess I should have put some G's somewhere. Right, and if this is like a finite group, then what's a G vector bundle on S? Well, it's exactly a representation of that group, okay, over your base. So you would have, of course, said, how do I get to the genuine stable category? You invert the representation spheres, there you have it. But now, of course, we're back to square one, because we wanted all the tomb spaces to be invertible, but I mean, okay, I should just call Mark and he proves that they are invertible. Okay, so that's the definition. So this is well behaved. For G tame. And I remember that probably in the previous theorem I should have had another condition, and the condition is that X is sort of vaguely reasonable. Where vaguely reasonable, of course, is not what Mark says, but for example, if it's finite, then it's just any scheme. And so in general, I think if it's G quasi-projective, then you're fine. So I'm going to leave this out here as well, just for being consistently wrong. So in particular, right, so this is well behaved. What does that mean? So certainly all these tomb spaces of vector bundles are invertible. And it has a 6 functors formalism. In particular, if you take a smooth projective scheme over your base, you look at its suspension spectrum here, then you get a strongly dualizable object. And you know what a dual is. It's like the tomb spectrum of the negative of the tangent bundle, something like that. So it exactly works like you think it works. You just had to do the right definitions and put the right adjectives in the place, and then usually you're good.
If I plug in x to point, I do get genuine.
You plug in x,
The point.
s. I mean, x will then be s, I guess.
Yeah, but s.
And s is spec k.
Do everything with point. Do I get genuine spectra back? Is it the same definition?
Genuine classical spectrum. No, it's just like if you take G trivial, then you get Motivic. I mean, the usual Motivic stable homotopy category out of this, which is not the classical homotopy category. Because, I mean, there are a lot of schemes in this.
Yeah, but if all the schemes are points.
But I'm working with smooth things over your base. So whatever you start with varieties. If you put in a scheme, like a field, then you start with varieties.
And I can view G as a finite group as a discrete.
Yeah, you can.
Over the point, right?
G, you can, yeah, but this, right, we're using these smooth schemes here. We're sticking all of them in. It's just way too many things. No worries. Oh yes, I wanted to give you a warning, which, okay, so everything works as you would expect, right? So better show you how it doesn't. So one of the first things that I learned about equivariant homotopy theory is that you can reduce it to classical homotopy theory by taking fixed points. That's one of the key structural insights. So if you have a subgroup, you can make a fixed point functor, you can make a geometric fixed point functor, well, you can definitely make a categorical fixed points functor. Not sure that I can make a geometric fixed points functor in complete generality, but often you can. For example, if it's G is finite, then we can do this. So we can make something like SHG of x goes to SH of H fixed points at x. Maybe it looks slightly funny, but it's just because often x has a trivial action, and then of course it's just remains the same, but well, to take fixed points like this, you have to take fixed points on the base. So you get a bunch of functors like this to the usual Motivic homotopy categories, and the warning is that these together are not conservative. And I guess it's a nice coincidence that these warnings are on the same sort of side of the room. And in fact, I think they're closely related to one another, although I would be hard-pressed to make an exact implication. But anyway, you got to be careful with this. It's not enough to check things on fixed points, at least not if you define fixed points in this way. If I have time at the end, and it's definitely not looking like it, I could maybe say something about that, what you can do instead. But anyway. So I was going on in the story, how everything works as you expect. So let me outline that, in fact, a lot of things work as you expect. And one important thing is the Tom-Dieck splitting theorem. And the cool kids, they call it the Gepner-Heller theorem. Jeremiah is even here, so well, I'm not sure what that means. But okay, so from now on, G is going to be a finite discrete group. And I mean also tame. So the easiest possible situation. And as I was saying, I can make fixed point functors. Maybe I will not assert this again, right? So certainly we have these fixed point functors. But maybe, well, it doesn't really matter. But for example, if you take the suspension spectrum of a smooth X scheme, it will be sent to the suspension spectrum of the fixed point of that scheme. So the fixed point really, well, let's have to the geometric fixed points. Anyway, it doesn't matter so much. I wanted to do categorical fixed points, so that's not so good.
So are there realization factors? So are there, like, if you look at over for x and s equals x or something?
Like if S is spec Z, then you can realize to the classical genuine G equivariant homotopy category. Okay, so I'm just going to say I can make so this is already a fixed point functor, I've asserted that, and I can make a geometric homotopy orbits functor. So I will denote it like HG, except I'm supposed to use a blackboard bold H to remind myself that it's some fancy thing. And let's say it starts at SHG of S. Okay, and so for simplicity, now I'm going to take the scheme to be the base scheme. You can, for what I'm going to say, there are variants also for X, but it gets more complicated in notation, and I want to highlight the similarities with the classical genuine equivariant homotopy theory, which is usually done in this situation here. I guess because every finite G set is actually a disjoint union of orbits, and then you immediately reduce to these kinds of things for various groups. Anyway, you look at this thing, and it will go to usual spectra, Motivic spectra. And just to give you an idea, this is induced by the following construction. Suppose I take some smooth S scheme with a G action. What am I going to do with it? Well, what I'm going to do with it is I'm going to view this as a presheaf on the category of smooth S schemes. And this presheaf inherits a G action, right, for some trivial reasons. So I can just take the homotopy orbits in the category of presheafs on smooth S schemes. And then what I'm going to do is I'm going to étale localize this thing. Now, if you've never seen this, this is like a very curious construction. Because, like, I mean, first of all, why does this do anything? And the reason why it does do anything interesting is because you build the category of motivic spaces using the Misnevich topology. So if you étale localize something, you're really changing the motivic space. But it turns out this is somehow reasonable. For example, if X is just a point, this thing will be what is called the étale classifying space. And Morel and Voivodsky have studied this, and they have proved that, in fact, this construction is something reasonable. And in fact, what they have proved is that you can understand this. So this thing is A1 equivalent, right? So in my category of motivic spaces, to something else which maybe looks slightly more reasonable. And what you do is you take X, now as a scheme, and you take the product with something which I'm going to denote by EGMG. So this is supposed to be a geometric model for, well, EG. So in other words, this is an in scheme which looks like it should be contractible and has a free G action. For example, if you take G equals C2, then you take A infinity minus the origin. That's like an infinite sphere. It should be contractible, and of course it has a free C2 action. And then I'm just going to mod out by the residual action. So it's exactly how you learn, I guess, in old school topology, how to do homotopy orbits. Yeah, you pass to some equivalent space with a free action, then you take the quotient in the usual sense. And it's exactly the same thing. You just do it on the level of schemes, which is, well, I don't know. That's how you do geometry. And then you extend this functor by sort of formal properties. So if you want to do it actually to spectra, this is a bit annoying, but anyway, these two spaces you can pretty formally extend this. The category was constructed in such a way that it's very easy to map out of. And yeah, you say what you want to do with the generators, you have to check some stuff, and then there will be a unique extension automatically. And now, with all of this preparation, I can tell you the Gepner-Heller theorem, which is that the Tom-Dix splitting theorem holds if you use this notion of homotopy orbits, and if you, yeah?
Is this right inside étale local?
Well, it is, this thing, of course, is by definition étale local, but it's not motivically local. So then you would take this étale sheaf, you view it as a presheaf again, and now apply your motivic localization factor. So after this procedure, it will no longer be étale local. So if I want to be super precise, I would have to...
So you make it again A1 invariant.
Yeah, exactly. So I would have to write like L mod here.
Okay, no, it's good.
I mean, in fact, this is a scheme. So it's also étale local. But again, I mean, they're not, even as étale sheaves, they're not the same, of course. But once you do L mode on this side too, then they become actually the same. Yes?
What do you mean exactly by the homotopy orbits in pre-sheaves or smooth sheaves?
Well, it's a in infinity category. I can take homotopy orbits there, but I mean, just means section-wise homotopy orbits.
What is doing the entire localization value that if you then use the equivariance of the
I mean, in some sense, it's just a slick definition. This, I think, sort of explains more, right? So this is very geometric, and Morel and but so the thing is, this geometric model is sort of not unique, right? You could imagine many ways of making like a contractible scheme with a free G action, and so you get various possible things here. And what Morel and Wygotsky prove is that no matter which choice you make, you're actually motivically equivalent to this one slick guy. So that just shows that this is well defined in some sense. Okay. I assume this countdown is how much time I have. So the theorem of Jeremiah and David Gepner is that if I take a motivic space with a G action, well, genuine G action, with the S, then I can look at the suspension spectrum, take my categorical fixed points, and what I get out is that direct sum over the conjugate classic classes of subgroups of these guys. Wait, I'm writing here HG, but I'm pretty sure I'm supposed to write Y group of H. Okay, my notes are wrong, but maybe I fixed it at the last second. So it's exactly, the formula should basically be the same as in topology. You just have to interpret all of the objects correctly, or like you interpret them in some other way, and then it's magically still true.
So shouldn't then this fixed point functor go to Y group equivariance?
Yes. You can make it, well, I mean, this exists, right? But yes, there's a better version which goes to Y group equivariant stuff, and you can forget down average.
So actually with those orbits you take, like how do you view G as, because G is a finite group scheme.
Right now it's just a finite discrete group, so it's literally a group in the category of sets.
Work over the field.
It's not over the field, it's just a group. Like, I mean, you just take a usual group, like sigma 5,
yeah.
And of course you can move it into the category of smooth schemes over any base by just taking finite disjoint union of them. Yeah. So this is a very, very boring group from the perspective of algebraic geometry. So I believe that this, so I should say something. I should not say things because I'm way too slow, but one of the things which I want to say is that the statement is exactly as in topology, but the proof is not exactly as in topology. So at some point you have to prove Adams isomorphism, or equivalently there's some sort of proper base change for morphism, which proper morphism between stacks, which is not representable. And these guys somehow do it, but it's very mysterious to me. I mean, I've looked at the proof and it seems right, but I don't know. It's very hard. I have no idea what's going on. So this is quite tough. Yes. When I first learned about this result, about genuine classical homotopy theory, I mean, I was like, okay, sure, this answers a lot of questions, but also it raises a lot of questions. I mean, this just, it feels wrong. I mean, like, not incorrect, but like, surely this cannot be the optimal formulation. And then later I learned a better formulation, and this is language of spectral Mackey functors. Okay, so classically, as you well know, okay, so there's this notion of a Mackey functor, and then there's a notion of a Mackey functor valued in spectra, and it turns out that's the same thing as the genuine equivariant homotopy category. And from this perspective, these formulas are much easier to explain. And also, it's basically easier to use even than this formula, in my opinion, so you don't even need the formula, but you can get this out. Actually, I should credit Markus Hausmann, because I always knew about this. Well, always. At some point I knew about this. I also knew about this, but I didn't really connect the two. And at some point he told me, well, yeah, like, how am I supposed to think about this? And he was like, well, it's basically the same. I was like, yeah, sure. And then, I think 3 years later, I asked him, you know, Markus, you know all this equivariant homotopy theory? I always found this and this is sort of useful, but how can I think about this? It was like, what are you kidding me? I told you it's the same. And I was like, okay, you're right. You're right, you told me this before. But then I realized, okay, we have this motivically. So can we get this motivically? And it turns out we can. Ooh, it's even turning yellow once I get that. Okay.
Wait until you get 5 minutes.
So, what am I supposed to do? Yes. So I'm going to define for you motivic spaces, motivic G spaces with finite étale transfers. Oops. Eager with the G there. And what I do is I do my motivic localization to P sigma on some correspondence category. So this is going to be a 2-1 category of spans. And the objects are the smooth G schemes with the X schemes with the G action. And then the backwards arrows are going to be the finite étale morphisms. And the forward arrows are whatever you want. So how does this relate to Mackey functors? Well, if here you put the category of finite G sets, then every morphism is finite étale. So this just means spans in finite G sets. And spans in finite G sets is how you get Mackey functors. So this is the motivic version of sort of space-valued Mackey functors. And you can get the following corollary of the Tom-Dix splitting theorem.
Sorry, Tom, what's the last word?
All. So any forward morphism that you want. So it contains the usual category of X schemes with a G action. So the corollary to the Tom-Dix splitting theorem is that actually this G equivariant genuine motivic homotopy category, you can describe it as follows. You start with the genuine motivic G spaces with finite étale transfers. And then you invert the trivial representation sphere. Okay, exactly like in topology, if you start with space-valued Mackey functors, you invert the trivial representation sphere, i.e. the circle, you get spectrum-valued Mackey functors, which is genuine G spectra. And so the same thing happens motivically. Now I'm saying corollary here is maybe a little bit liberal, because yeah, this is the theorem, and you want to get to this theorem is not as easy as I would like it to be. So right, so I mean, how does this possibly work? I've been warning you that the fixed points, the obvious fixed points, they don't give you enough fixed points to have a conservative collection. But the way around this is that, I mean, you just make much bigger families of fixed point functors, and then you read their paper correctly, and you realize they're not just saying this, they're saying but something much more general, which also applies to all of these other fixed point functors. So basically, that's, in some sense, the starting point. But there is something else, which, I mean, is at least a cool fact, but also not entirely obvious, is that what this tells you in particular is that this category of genuine G spectra is generated by, you just take suspension spectra and then you desuspend by the trivial representation sphere. And this is not at all obvious from the definition. Okay. In fact, I mean, in classical genuine equivariant homotopy theory, if you do this like for a positive dimensional group, it's also not immediately obvious, but you can prove it. And also here you can prove it basically by using some variant of isotropy separation, which was also pioneered by these guys in the Motivic world. But you can.
So you don't construct A1 on the right hand side?
Well, for sure. It's got to be in here. Did I define this at all? Yes. So no. Here, there's an L mode there, so this contracts A1. Yeah, definitely. Contract A1. Okay, but you can prove this using some sort of isotropy separation, which is again something which is not obviously available, but you can find some sort of analog which helps you. And I'm rapidly running out of time, so maybe.
So just to clarify, now G is also like finite.
Yes, it's still finite.
So you mean your theory does it's not obvious your theory extends to finite group schemes?
No, it's not obvious.
Okay.
So I believe that the Gepner-Heller theorem should hold for finite étale group schemes, but I haven't seen a proof actually. But probably more or less the same proof. Jeremiah is nodding. For general finite even tame group schemes, so something even like mu p and characteristic p, I'm not really sure what to expect. Yeah. So maybe for my last 3 minutes and 33 seconds, I will tell you something. Yeah, I'm going to skip the fixed points, unsurprisingly, but I will tell you about the T structure, or a T structure. Right? So, I mean, one useful thing in homotopy theory are the homotopy groups. And pretty uncontroversial statement. And in genuine equivariant homotopy theory, you also have the homotopy groups, except that they are Mackey functors. So you have the homotopy Mackey functors. Correspondingly, you have a T structure on the genuine G spectra, and the heart is the Mackey functors. That's pretty useful because, yeah, I don't know, you know how to use these things. And so then we can do the following definition, which is inspired by taking the definition of the homotopy T structure, which is sort of the best T structure which we have on the usual Motivic category, Motivic stable category. And you use this thing here, right? It's generated by the suspensions and then desuspend by the trivial representation sphere. So I define SHG of S greater than or equal to 0 to be the subcategory generated under colimits and extensions by these guys. Not these, well, okay, so I'm going to write sigma infinity of anything tensor GM. Okay, you don't take P1, you take GM. Some magical observation of Woiwodsky and Morel that this somehow classically gives you something very good. Well, I guess I'm not going to be writing much more, but I just want to make some notes that this is very well behaved. For example, in classical genuine equivariant homotopy theory, this is TX. This commutes with taking fixed points. So, for example, very well behaved. So it's usually complete. The usually here just means if you take some humongously large scheme, then you can run into some problems, but finite dimensional QCQS schemes, for example, then mod out by a finite group, that's fine. Then the fixed point functors are exact. I've run out of pages to look at, but I think that's what I wanted to say. Okay, and the last thing which I want to say is that if G is C2, and S is the spectrum of a field of characteristic not true, then I can describe the heart. So I clearly don't have enough time to say this, but if you know the usual homotopy T structure, the heart is so-called homotopy modules. And basically here it's homotopy modules again, but what you have to do is you have to build in the finite étoile transfers, right? I'm going to use this result. Yes, and I think this is true for more groups than C2, but I'm not sure for which groups this should hold. So I've written it for C2. I think it will hold for any group such that all representations are sums of one-dimensional representations. So then at least my proof, I think, will work. If you take another group where there's like positive, I mean, the dimension at least 2 representations, I don't know, maybe it's true, maybe it's not true, no idea. And minus 38 seconds, so I gotta stop.
Questions for Tom?
I don't know.
Okay.
Go for it.
Barwick has this other version of tonic splitting for coherent topoi. Like, does this fit here? Is this category over there still a topos?
Which one? This? This is a topos?
Yes, of course, but then above this G space is actually out.
No, definitely not a topos. Sorry. But also, I do not know this result in Barwick, so I don't really know the answer.
It's in the appendix to Spectra Mackey functors.
Ah.
So you said that you expect this to work for group scale representations with some. So, like, are you saying that in your proof that's all you use, or?
I think in my proof that's all I use, yes.
But just for knowing, like, why C2 that, or, like, you just haven't written it down?
Well, I mean, that's the easiest group, right? And I mean, I was trying to work this out, and I mean, this requires, like, to me, quite hard algebraic geometries. And so, I mean, once I could manage to do this, I wanted to write it to be sure. And then I sort of couldn't really be bothered to change it to this, like. But I think, again, as far as I have checked, it will work whenever all the irreducibles are one-dimensional.
Maybe you already answered this question and I missed it, but could you tell us how the Tom-D splitting is the same as Spectra Mackey is the same comment?
I do not think I can say something coherent right now, but it's just if you, what am I doing? If you look at this sort of formula there, you have like these sums over conjugacy classes of subgroups and so on. So exactly you sort of see maps in this category of spans of finite G sets. And if you soup it up enough, you can see that these things are very closely related.
So quickly check. So here, your definition, you just done T-structure definition.
Yes.
Your n could be negative, right?
Yeah, definitely. You need to take n negative. I mean, n positive, of course, is very boring.
And I wonder how this theory extends to derived schemes.
You and me both. I mean, there's this work of, I think, Adil and Charanya, and I think they probably like do derived whatever stack as derived as you want. So some of the things you can write down in extreme generality. You cannot prove so many things in extreme generality, and I don't know what exactly you can prove about derived schemes.
I think they prove it's truncated.
Okay, so that's one thing, which is good.
Were there more things about the fixed points that you were?
Well, I mean, sure. Yes, so in general, it's not enough to take like fixed points for all the subgroups, but you can make interesting lists of sort of fixed point functors. Maybe the easiest thing I can tell you is if you take C2, then you sort of SHC2 of K maybe. So you go to the underlying. So this is fixed points for a trivial group, I guess. And then you go to, wait, what am I doing here? This is underlying, and then you go to SH of K, which is C2 fixed points. But there's something else which you can do, which is you look at some disjoint union of fields. So if our finite product of fields, maybe I call this L over K, and I give this a free C2 action. But it doesn't have to be like a finite extension, something like that. And once you do this, like let's say you pull back to this L thing with a free C2 action, and then SHC2 of L is actually the same thing as SH of C2 fixed points by descent. And so there's something else which you can do where you start here, you go all the way to here, and then you go to here. And these things together form a conservative collection. So this is some sort of way of sort of twisting twisting by a free thing. And all of these together are a conservative family of fixed point factors. And there's a generalization of this to arbitrary finite groups, finite chain groups.
Let's thank Tom again.